Howdy, and welcome to Team Cirrus Capstone Project. The team and I will be covering the following topics today, beginning with design and testing and closing with collaboration and impact prior to a Q&A. It's my privilege to begin the introduction of the team. John Locke, Project Manager.
Michael Craig, System Integration Testing Engineer.
Ryan Milford, Mechanical Design Engineer.
Natalie Rupi, Project Feasibility and Quality Engineer.
Cesar Andrade, Additive Manufacturing Engineer.
Jacob Morrow, Project Coordinator and Manufacturing Engineer.
Our partner electronics interface was Team Icarus from the MXCT and ESET program.
Our team stakeholders were sponsors Dr. Joseph Morgan and Professor Matt Leonard, and NASA customer Dr. Mark Fries.
The purpose of this project is to design, build, test, and implement a purely mechanical subassembly that will collect and safeguard cosmic dust particles from contamination throughout the entire duration of its flight. The assembly will be coupled to the motor output shaft of an electronics interface. After landing, NASA scientists will be able to collect and analyze the cosmic dust particles gathered by the subassembly.
The drive shaft of the subassembly shall couple to the output shaft of the control module's motor.
The collector enclosure shall open upon rotation of the system and expose the collection pads with a surface area of 15 by 15 centimeters.
Upon activation of the motor, the lever arm shall extend to a pre-calculated 1 meter fixed position.
The less than 10-pound subassembly shall operate between -40 and 120 degrees Fahrenheit while rotating in either direction at 100 RPM.
For our final model will include aluminum 6061, carbon fiber, polycarbonate, and Teflon.
This design was constrained to be a completely mechanical subsystem to improve the reliability of operation. At the same time, our team worked closely with our partnering electronics team, Icarus, to ensure compatibility between the control and collection subsystems.
Fusion 360 provided 3D modeling capabilities to create our design, animations for visual demonstrations, and 2D drawing functionality for fabrication requests.
After creating the 3D models, we used Cura to slice those models and prepare the G-codes for 3D printing. Printing allowed us to stay on schedule by creating the necessary parts to complete the prototype quickly and cost-effectively. By controlling things like infill, wall count, speed, and bottom and top layers, we were able to control the quality and time necessary to complete a print.
It was evident that with the number and complexity of custom parts needed, it would not be feasible to manufacture them ourselves using university machines before the end of the semester. We first reached out to third-party machine shops around Texas, but received high-cost quotes out of the desired budget of the project. It was then decided to utilize the FEDC's fabrication request process on campus, which only requires the purchase of raw materials. It was then only necessary to submit engineering drawings and model files to the FEDC, and material orders through our sponsors in order to manufacture the 85 total parts. This approach allowed for minimization of cost without sacrificing lead times.
Throughout our time, the team created many early models and concepts that were likely to achieve the desired function of the mission. After working out calculations and making necessary changes, a prototype of the design was printed and built that was tested as shown here. The prototype was a pivoting lever arm that used a simple extension spring attached to the top of the enclosure arms. This design in theory was mathematically and mechanically sound. The prototype was made from PVC and 3D printed components to allow for modifications to be done quickly and to reduce the cost of testing.
The feasibility of the centrifugal pivoting concept was confirmed with our testing, but the team realized many improvements needed to be made for the final design to ensure reliability and effectiveness. Shown here, the final iteration implements multiple springs in multiple locations to improve actuation and the slack within the system that can be seen in our prototype testing.
To ensure low friction movement between moving parts, as well as to eliminate the likely risk of contamination from liquid lubricants, Teflon bushings between the main shaft collars and Teflon rails are used for the material's low outgassing properties and low temperatures. A major feature of the assembly is that the collector arms allow rotation in either direction. The symmetrical nature of the subassembly removes the need of complex and redundant components, which decreases the need for adding weight to balance the arms during operation, while additionally increasing the allowable weight for energy storage within the motor control module.
The last critical feature during the operation of the subassembly is that the enclosures can collapse and return to the protected stored position in a power loss event. This is an advantage of the team's fully mechanical assembly to allow for the longest collection periods as possible and to ensure safe sample collection for future research studies.
As the team worked through design iterations, two major focuses were towards spring extension distance and weight savings. Our design combines unique geometry and strategic material selection to shed weight in unnecessary areas. The team worked with the shop leads at the FEDC to optimize each part such that they are light and easy to manufacture. This allowed us to achieve an estimated weight of 9.1 pounds in the flight-ready model, which is less than the maximum 10-pound limit. The spring constants placement and actuation method was chosen to create the minimum distance possible required for spring travel. To accomplish this, the central shaft holds a housing that combines 2 extension and 2 compression springs. The extension springs pull the enclosure arms halfway to their upright position. From there, the compression springs push the rest of the way until the arms are locked and vertical. This combination of spring force is strong enough to hold the enclosure upright while still allowing the centrifugal force from rotation to push the arms down into their operating position.
This team is diverse in several ways. This allowed great balance in approach and communication, with a healthy team nucleus being formed on Zoom despite the restrictions of COVID-19. A professional nature with a cultured environment existed on all 3 platforms we use as a team for internal and external communication. Microsoft Teams was an easy choice as an internal collaborative platform. The team exploited its services to manage documents of all types from a central, editable, and trustworthy software. This evaluative process required technical decision-making at every level of this project. Team members continuously and coherently made well-informed, project-mindful decisions with a goal to finish on schedule and on budget in mind with every step.
This project was a unique opportunity for us as students to experience a workplace-realistic team environment. To achieve success, team members had to master external communications for raw material ordering, manufacturing requests, and delivery of finished goods. In the words of Professor Leonard, this project was an instrumental learning experience because it allowed students to come together in a multidisciplinary fashion to create a project that satisfies the customer needs.
The team's lesson learned and scheduling were in coordination with our original assumptions on lead times for manufactured items. When sponsors decided to use the FEDC as a manufacturing source, the team agreed to present several shifts in the timeline. The original deliverable date was an eager early one in late March, but of course the schedule included buffers and milestones which accommodated things like diminished lead times due to COVID and increased timing setbacks like the snowstorm.
Through utilizing the FEDC, our team was able to keep the overall cost of the project at a minimum. In reference to the cost, quality, and speed triangle, this led our project to lean in the direction of cost and quality while experiencing longer lead times due to the immense number of projects that the FEDC was currently carrying out. With recommendations from our sponsors, our team strategically ordered some of the parts to be 3D printed in addition to the fabrication requests to ensure that a non-flight critical model could be delivered by the close of the semester. Many lessons were learned in regards to the relationship between time available to deliver the product, the quality, and the available resources, which, in the words of Dr. Morgan, are typically beyond single capstone team exposure.
The result of the high-strength materials combined with a folding stow system produces a high potential for reusability without heavy maintenance required by the customer. In comparison to the previous flight collection method, the subassembly will save thousands of dollars per flight, while also delivering a far less contaminated collection surface, allowing the customer to more efficiently analyze the returned cosmic dust. The new method can stay on mission for a month or more before returning to the ground, while the replaced method can only collect for a few hours before returning the samples. The total cost to fully complete the non-mission critical and mission critical models is shown here. The decision to reuse all hardware and main shaft components in the final model was a crucial factor in minimizing the total cost.
I'm Dr. Mark Fries, and I am the curator for NASA's Cosmic Dust Collection. The instrument that this team is building will be used to collect dust from the Earth's stratosphere coming down to us from asteroids and comets, and it will be made available to the world's researchers to request and study in their laboratories.
Howdy, my name is Matt Leonard. I'm the President and CEO of Texas Space Technology Applications and Research. Cirrus did a great job of coming up with a very innovative solution for the problem, as well as persevering through several struggles with getting the design implemented and then actually made. One of the best parts about this to me is Cirrus actually came up with a working prototype. The other part that's really amazing about it, this is one of the first times I've seen capstone teams have to work with other capstone teams in other disciplines, as well as working with other teams that were building rotating arm assemblies. Throughout that, Cirrus did a great job of communicating with all the other teams on what their requirements were and how they were going to interface with them.
To close, we would like to thank our amazing sponsors and the university for this unique opportunity to collaborate on this project with NASA and T-STAR. It is so rewarding to have been able to design and produce a subsystem ready for flight, and we look forward to seeing our project in action.